Hi, my name is Joe Hellerstein. I'm a professor of computer science at UC Berkeley, as well as the co-founder and chief strategy officer at Trifacta, the data preparation company. Today I'm going to talk about the art of the state, serverless computing, and distributed data. To talk in 4 chapters, the first chapter we'll look at is sort of the state of serverless computing today. Then we'll talk about one of the key issues in performance and correctness of distributed systems, which is avoiding coordination, and the calm theorem, which tells us when exactly we can correctly avoid coordination. And then finally, I'll talk about work going on in the RISE lab at Berkeley now, the Hydro project, topics like stateful serverless computing and beyond. So there's a saying sort of in computer science that every generation of platform gets a programming model that unlocks the power and potential of that platform. So famously, the PDP-11 and the mini computer got C and Unix, and Thomson and Ritchie's Turing Awards were around the idea of them unlocking the power of mini computers by developing that programming environment. And we saw analogous things in supercomputers, for example, with the Chapel language, in graphical programming and personal computers with the WIMP interface, and most recently, of course, in smartphones, where new programming environments have made it easier for application developers to develop an app for that in ways that no one ever would have expected would run on a telephone. Now, another platform that arose around the same time as the mobile phone was the cloud. And yet somehow the cloud doesn't have a programming environment that is native to it, that enables people, third-party developers, to produce things we never would have expected. In some sense, we're still waiting to hear how will folks program the cloud in ways that foster unexpected innovation. And keep in mind, there's good reason for this having taken a while. Distributed programming is really hard. It involves all the difficult issues of parallel computing, as well as the difficult issues of distributed computing, like consistency of data, partial failure, reordering of messages, and then the cloud aspects of auto-scaling, for example, of fleets of computers growing and shrinking while your application is running. That makes it even harder. So it's a tough environment to program. Now, I've been talking about this for over a decade with researchers and colleagues at Berkeley. And we've gotten lots of attention for our work in academia and laid down what we think are a lot of foundations. But we're just now beginning to see the industry waking up to the idea of programming the cloud. And in particular, this is embodied in what's called serverless computing, which came out in the last 5 years or so. And you can see that it's becoming quite popular in the community, even more popular than MapReduce at its peak, if you remember your trends from about 5 years back. So what is serverless computing? Well, it's usually presented to users in the form of functions as a service. It's an idea for allowing developers outside of the cloud platform to program the cloud, give them access to thousands of cores, petabytes of RAM, and allow them to have programs that have fine-grained resource usage and efficiency as their application needs change, so that the envelope of how long you have machines versus how much load your system have are very tight. You usually have just exactly the right number of machines for your load. This sort of a payment on demand, allocation of resources on demand, enables new economics, new pricing models that give different incentives both to the cloud vendors and to application developers. So very exciting to see it beginning to happen. And if you've never seen a functions as a service interface, here's a simple one from AWS. You can register a function at the top. In this case, it's in Python, but you can pick your language. And that sequential function can be executed in the cloud by sending it a remote request over, say, a REST endpoint. And you can see a result here at the bottom of one of those executions. So very straightforward. This function just happens to run in the cloud. Now that's nice, but we published a paper about a year and a half ago and presented it a little over a year ago at the CIDR conference that talks about what's missing from serverless computing today. We call it 1 step forward, 2 steps back. And basically what we're excited about, that step forward, is the idea that the cloud provides this auto-scaling platform. I can write a piece of code and it will get as many computers and as much resources as it needs to execute for whatever size workload it currently faces. Really, really exciting game changer for third-party programmers. What it doesn't offer is any of the features that make the cloud so great. You can't get access to massive amounts of data, and you can't build unbounded distributed computing programs with the current state of FAST. And so it's tantalizing and yet terribly handicapping because we really can't do the things that are native to the platform. Lots of data, lots of interlocked compute. Why doesn't it allow us to do these things? Well, there's three key limitations. The first is enormous I/O bottlenecks for fast functions. Your code that runs in Lambda or in the analogous offerings from Google and Microsoft sees 10 to 100x higher latency to storage than a simple SSD. And you are charged for each one of those round trips. So terrible disincentives to doing I/O. You essentially cannot run I/O-centric code in FAS. And we measure this in the paper and demonstrate the costs. Now, fast functions, the whole ethos of serverless is you should not have servers, including server software, which means that after about 15 minutes, they're going to kill your code no matter what it's doing. So because functions routinely fail, we can't assume any session context. They also don't have storage. So when your function goes down and it comes back up, which it will do, it's forgotten everything it ever knew. Okay, so no context across these short lifetimes. And then finally, there's no inbound network communication allowed for these functions. This is probably the most critical limitation. So these functions cannot actually talk to each other over the network. You cannot do distributed computing over the network. The only way around it is for you to put data into storage and have another cloud function read that data from storage as a crude form of sort of blackboard computing or communication. So this communication is, of course, very slow and very expensive due to those I/O bottlenecks. So in essence, you really can't get good access to data, and you can't have these things talk to each other. So goodbye data-centric computing and goodbye distributed computing. All right, so we talked a bit about the state of serverless. I'm going to shift gears and talk about some fundamentals today around avoiding coordination that'll explain, in some sense, why they've postponed these harder issues in the current FAS offerings and what's going to be challenging in the work we're doing to do stateful serverless computing. So a first step in making these fast functions better is to make them stateful. That is to say, to allow them to have state that persists across runs. So of course, program state is really data, right? It's the data that's managed across invocations of a program. And the challenges of managing data in these massively distributed auto-scaling systems are twofold. First, there's data gravity. It's expensive to move state around. You want to make sure your code and your data are co-located when they run. And this is kind of a scheduling problem or a policy problem. And I'll assert that it's not that hard. We have scheduling algorithms. We can figure this out. It's sort of one of those fine-tuning issues in computing. We can get this right. The second issue is much more challenging, which is distributed consistency. This is a correctness problem that if we don't solve, our code won't work, or it won't work reliably. It's difficult. It's very tricky, and it's unavoidable because we have distributed computers that can't talk to each other. So let's talk about consistency and just review classically what this means to distributed programming. So the goal with consistency is to ensure that distant agents, like these two nice folks in the upper right of this slide, agree, or at least that eventually they will agree, on common knowledge. So in this case, they both agree on the value of a variable x, which in the current case is love. They agree on love, and that's lovely. But how do I know they will agree on x if it's a mutable variable, if it can be changed over time? So in this case, on the left-hand side, an update has happened to x that the right-hand side hasn't seen. And so the poor guy on the right-hand side still believes love, but the truth on the left-hand side is more like poop. And if they don't agree on x, imagine all the other things they won't agree on going forward until they're co-located and can communicate again. So this idea of having computations that are running independently and disagreeing on variables is sometimes called the split brain problem. And the further they get from each other's original shared state, kind of the more hard it is to put back together. So there are classical mechanisms to fix this, and classically the mechanisms are categorized in a category called coordination. So this includes protocols like consensus. There's a picture here of Leslie Lamport, Turing Award winner who invented Paxos. Transactions in databases are another form of coordination to achieve agreement. So transactional commit, like distributed commit, two-phase commit, is an example that we use in database systems to get consistency. These are tricky protocols. So every time I have to teach Paxos, I have to read up on it and make sure I get it really clear to explain to the students. It's tricky stuff, but worse than that, it's also bad stuff. Don't use it. Let me tell you what I mean. For this, don't trust me. I'm going to use one of the heroes of modern cloud computing, James Hamilton. If you don't know James, he goes way back. His original job was a motorcycle mechanic, and then he worked at IBM, he worked at Microsoft, and he was one of the key architects of AWS. And he, more than anyone, has lived through the evolution of warehouse scale to global scale computing. And he said at a cloud computing workshop about a decade ago the following, which I like to recite as poetry because I think is beautiful. The first principle of successful scalability is to batter the consistency mechanisms down to a minimum, move them off the critical path, hide them in a rarely visited corner of the system, and then make it as hard as possible for application developers to get permission to use them. I like to paraphrase this as saying, thank you, Dr. Lamport, for all the Paxos, but we don't want to use it. All right? Why is James saying that people should not be using these techniques that are the techniques we have for coordination? Well, waiting for control is bad. If you're in a distributed system, the bigger the system is, if you're waiting for everyone else, the higher the probability that someone else is slow. So what seems to be the attraction of cloud computing, which is that you can have really big numbers of machines, if you use coordination, that becomes the curse of cloud computing. That big number of machines means that waiting can be really long. Okay, so these straggler effects or the tail latency of a quorum of machines is typically very high as you scale up. So you really don't want to be waiting because you're typically waiting for somebody who's slow. The other issue with waiting is it leads to what are called slowdown cascades because of queuing. If you're waiting for someone else, odds are somebody is waiting for you. So it's not just your problem if you decide to wait for someone. It's also a problem downstream of you, of everybody who's affected by you. And this is why James is saying that regular programmers should not be given access to these coordination primitives. They should not be allowed to wait because of the cascading knock-on effects of that decision. So how do we solve this problem? Obviously, we need our systems to be consistent if they're going to make any sense. And the sort of critical insight in a lot of the work that's been going on over the last many years, especially in my group, is to kind of raise the level of abstraction from IOs to application semantics. So traditionally in distributed systems and distributed databases, all we seem to care about is IOs, even though what we're building is applications. So, with thanks to my former student Peter Bayless at Stanford, here's a picture. It's an old Far Side cartoon. It's been adapted to the moment. On the top, we have our application semantics. Okay, database, be good and move one iPhone from inventory to Bob's cart. But what, our database dog hears when we utter that is blah, blah, read X, blah, write X, blah, blah, read Y, blah, blah, write Y, right? They don't actually understand what we're saying. They just understand these keywords. And we're doing all our coordination to control this sequence of keywords, not thinking about what we're doing in the values that we put in these reads and writes and how they affect our programs. So maybe if we think about that, we can do better. So suppose that you do understand your program semantics. Which programs exist that might actually have a coordination-free implementation? These are programs we'd love to run in the cloud, right? Because they're coordination-free. All the other programs are programs that require coordination. And these are programs outside of the green circle that we'd rather not let developers build and run in the cloud. We have to be very careful with these programs to make sure that we don't try to scale them in ways that they won't scale and that we don't wait for them, right? And so this question, what's coordination free and what's not coordination free? Or if you prefer, which programs are red, they need all that Paxos and two-phase commit and nonsense, and which programs are green, we like them. We don't need any of that hard distributed system stuff that makes us go slow. And to keep in mind, this is a question of computability, very much like what is decidable or not decidable. What is decidable in a coordination-free language? What programs can you utter in a coordination-free language? And what things can't you? So this question hadn't been answered during all these years of development of protocols like Paxos and two-phase commit. No one ever stopped to ask when we can avoid them. And that leads us to the Calm theorem. The Calm theorem says that a distributed program P has a consistent and coordination-free distributed implementation if and only if it's monotonic. That is to say, the green circle on the previous slide is exactly the monotonic programs. That's the sharp line between green and red is whether or not a program is monotonic. Okay, but what do we mean when we say a program is monotonic? Well, pretty simply, monotonicity is the property that if the input to the program grows, then the output to the program grows. And in particular, what that means is that if you're running a program and it gets more input, it only will produce more output. In particular, it will never need to retract an output that it gave for the subset of the input. So think about what happens with a non-monotonic program. If it's receiving input, it cannot send it to the output because it doesn't know if something's going to come along that would cause it to change its mind about a potential output. So non-monotonic programs have to wait till they get their complete inputs to decide what are legal outputs. By contrast, monotonic programs can start producing outputs immediately when they get inputs. Intuitively, then, this is why monotonic programs can run without coordination. They don't have to wait for anyone to start producing output. They can just get to work. So in this month's CACM, September 2020, we have an article, myself and Peter Alvaro, where we go through the Calm theorem, give some of the roots, and explain the proof of the theorem in just enough detail that it can be understood by a typical computer scientist. We also talk about how calm thinking can affect the way we think about building distributed systems and perhaps the programming languages that we build for distributed programming. So you might say, that's interesting, why should I care? Which is a good thing to say to an academic when they present you their cool theorem. Well, we've been demonstrating that in my group at Berkeley. So calm thinking, if you really embrace monotone programming, you can build some crazy fast, infinitely auto-scaling systems. Because when there's no coordination, when no thread ever waits for any other thread, you get insane parallelism and very smooth scalability. Everybody is always just doing their job, heads down, never worrying about what anyone else is doing. Every thread is working. And we'll see this in the ANA key value store in a few slides. All right. We can also check the monotonicity of programs syntactically. We can actually have a compiler that helps us with our distributed computing and says, look, here in your program is a place where you're using a non-monotone construct. That's going to require coordination. Are you sure you want to do that? Now, unfortunately, we can only check this in languages that have monotone and non-monotone operations well separated. SQL is a great example of such a programming language. Won't have time to talk about it today, but the non-monotonicity in SQL is very clear. Operations like not in, anti-join, except. Okay, we developed a full-fledged distributed programming language based on many of the ideas that come from languages like SQL called Bloom. And you're welcome to have a look at it. The Bloom language is a distributed programming language that allows us to check for this monotonicity. The other thing for those of you who are fans of distributed systems is the Calm theorem essentially is a drill down or an explanation of the CAP theorem. Essentially what it says is that the CAP result is all about non-monotone programs, about the full space of potentially non-monotone programs. But the Calm programs, the ones that are monotone, actually can enjoy all three of consistency, availability, and partition tolerance at the same time. So CAP, in some sense, doesn't hold for the monotone programs. It only holds for the non-monotone programs. And this is explained in that paper in this month's CACM, and I'll refer you to that. Okay, having spent a little time on the Calm theorem, we can see that there's at least a theory now that says monotonicity is that bright line between what can and cannot be done coordination-free. We'd like to stay inside the monotone circle, but if we have to be outside it, we know what we're doing, and we know that we need to be there. Okay, with that, let me talk about some practical work going on in my research group at Berkeley. So Hydro is a platform we're building for programming the cloud. We really believe that the larger problem here is to let third-party developers easily write programs that we can scale up and down, auto-scaling with the full power of all the compute in the cloud and all the storage. And it's a multi-component system. It's a bit of a stack. We've been building it bottom up. At the bottom is the ANA key value store, which has been an award-winning paper at a couple conferences. On top of ANA, we've built our own functions as a service serverless platform called Cloudburst. Cloudburst, again, appears in the literature. And I'll talk about both of those today. The research going forward is actually pushing further to build a full cloud compiler toolkit and language, intermediate representation language for the cloud, where you can have many of today's popular programming models for distributed computing, plus possibly new ones that might be more effective, and then compile them to a common runtime that we can auto-scale and make efficient in the cloud. So that's the vision. Today I'll talk about the two components building bottom up. So ANA is a serverless key value store. It's an any scale system. We coined that term because of a quote from Jeff Dean, where Jeff asserted that every time your system scales up by 10, you need to re-architect it. And we said, that's crazy. That won't work for us in an auto-scaling universe of the cloud. So we want something that'll perform on a single box as fast as the fastest single box KVS, something like Redis. But we want something that'll scale across the globe like systems that are scaling, like S3. So can we build a key value store that outperforms at both of those scales? And the way we do this is by having column consistency baked into this system. The whole system is built out of simple lattice data structures. And if you read the paper, you can learn about this. And those lattices are all monotone, so they never have to wait for each other. This allows us to auto-scale the system, adding nodes very smoothly without performance hit. It also allows us to multi-tier the system. So you can have a disk tier of ANA, where everything is persistent on disk, and a memory tier above it of ANA that is like a sort of caching layer. Okay, so it's more like a cache use of a KVS. And these two interoperate seamlessly to give you a global multi-tier distributed store. So as I said, I'm real super proud of my students because they won Best of Conference at 2 straight conferences with their papers on the ANA key value store. It really is impressive work. So let me share a little bit about the performance of ANA. First of all, this system is a shared nothing system at all scales, even across threads. So every thread has its own state that it manages. It's sharded across these threads. And as you can see, they're totally coordination free. So as you add more threads, the system scales linearly up to 32 when you fill up a full machine of threads and you move to the next machine. The 33rd, 34th, 35th thread are now on a second server. And when you get to 64, we add a third server. And you'll see that the system scales linearly whether you're on a single box or as you start to span across multiple boxes, because every one of these threads is just doing its own work on its own shard and worrying about its own business. Now, under contention is where this makes such a big difference. So we're comparing here to 2 systems, Mastery, which is a system out of Harvard, Eddie Kohler's group. It's one of the fastest key value stores in research. And Intel TBB, that's Intel's thread building blocks library. This is their concurrent hash table that they run on their shared memory machines. So both Mastery and TBB are single node machine systems. They do not scale up beyond one server. But you can see that under contention on a single server, ANA is up to 700 times faster than Mastery and TBB. And I'll let you know that in a geo-distributed deployment, ANA is about 10x faster than Cassandra, which is a sort of typical geo-distributed key value store. Why is ANA so much faster under contention? Well, it's because we have coordination-free consistency. ANA never waits, even when reads and writes are hitting the same key. There's no atomics, no locks, and no waiting ever. And so if you look at this right-hand side, what you'll see is that ANA, even under contention, is spending 90+% of its time serving reads and writes, doing its job. Whereas all of the other systems are spending over 90% of their time waiting, essentially trying and failing to get atomic instructions through. ANA is going to do this with rich consistency. So it is actually able to achieve consistency levels that are stronger than many of the systems we compare it to. Now, Cloudburst is the stateful serverless platform we built above ANA. And the question we were asking is, can we avoid the problem of having to go round trip to storage every time you compute, while still allowing the compute layer to be disaggregated from the storage layer, so that we can scale up the compute as we will, we can scale the storage as we will, but the two are decoupled. Very important design principle for cloud and auto-scaling. And the main challenge here is now not only do we have to make sure that the distributed storage is consistent, we have to make sure that the caches are consistent with storage and consistent with each other. So in particular, suppose you're computing a serverless expression like g of f of x of y. The way this works in a fast system is f gets scheduled on one machine, f of x, g gets scheduled on some other machine, and g needs the output of f, which means that whatever's on the cache at g's node had better be consistent with whatever's on the cache at f's node. So those two caches have to be made consistent with each other. And so we developed protocols called hydrocache, which give new consistency for these distributed client sessions and allow us to get pretty nice consistency models for the programmer, even with these performance optimizations for stateful serverless. So as one example, and we've got many, as one example of an application that can benefit from this, where we've measured it, prediction serving. So the idea here is that you have a machine learning model which you want to put in the cloud. And the simple function of that machine learning model is it gets input, that is to say features. It does inference, it runs a machine learning model to predict some new output, right? And so very natural for functions as a service to put AI models in the cloud for prediction serving. And so what you're seeing here is bar charts of performance of latency for running the same model in native Python on a single node where the requests are coming just over the network to that one node, running it in Cloudburst, which is almost as fast, running it in Amazon's custom system for prediction serving, SageMaker, where it's quite a bit slower, and then running it in AWS Lambda, where it's terribly slow. And the bars are the median performance, and the whiskers are the 99th percentile of performance, okay? And so you can see that Cloudburst is almost as efficient as local computation and doesn't even suffer that much from variance in its tails. Okay, we have lots more applications, as I said. So we've been building serverless data science platforms on top of Cloudburst, including a parallelized version of the Pandas library called Modin that Devin Peterson's in charge of, as well as Jupyter serving Jupyter notebooks Charles Lynn's been working on, where you can close your notebook, your Jupyter notebook, open it up 3 days later, and it will spin back up in the cloud and run. Jeff Ishnikowski's a postdoc in Ken Goldberg's robotics group at Berkeley. He's been working on robot motion planning and using Cloudburst so that robots, which have limited onboard computation, can burst up into the cloud and run quick computations on hundreds or thousands of nodes to make planning decisions as they're moving their parts around in the room. And then finally, a host of undergrads and master's students at Berkeley have been building this examples of prediction serving. So they've got a whole bunch of different models they're launching at Berkeley called the Model Zoo, where you can go in and interact with these models, get predictions, see them run, and that's all running serverless. So when no one's using it, we're not paying for it. When it's popular, it scales right up. Okay, so those are just some of the examples that we're building on Cloudburst. So I've given you a flavor of what we're doing at Hydro, some of those applications, how we get cache consistency, and underneath it, how we get this extremely auto-scaling, high-performance storage substrate called Anna. But this doesn't really answer the big question I posed at the beginning of the talk. Have we figured out how to program the cloud? I'd say what we're doing just right now is pushing the state-of-the-art in FAS. But stateful FAS is still a limited API. It's just sequential code, like a Python function, with explicit reaching out to storage, in our case, to cached storage. But we're really getting very limited contracts from the programming language here. If you want your fast functions to talk to each other in Cloudburst, they can, which is a big step up from Lambda. But we're not helping you reason about whether they're consistent when they do that. The developer still has to reason about that in a fast environment. And then they need to decide when the app logic needs to coordinate based without any help from sort of the Calm theorem or analysis of monotonicity in your program. So the real dream is going to take time, and that's what we're building up in this stack, is we're trying to bring all of those ideas of the Calm theorem up to the programmer in a familiar programming model, or perhaps, if necessary, in a new programming model, so that we can compile down to this fast runtime that we've now built to have it be in an auto-scaling environment. So I'll close by thanking my collaborators on this work, graduate students Chenggang Wu, Vikram Srikanti, Charles Lin, and Johan Schleiersmith, and my colleague on the faculty at Berkeley, Joey Gonzalez, who co-leads this project. Thanks.